Welcome back, everybody. So before we continue, I would like to come back on something that one of you has made me aware of, and actually you had a point, so thank you for that. Here, there is something that I missed and I should have included, and that's the length. I should have put normally in the conjunction here that the length is at least one, condition on the length being at least one, condition on also the length being at least two, at least three, at least four. I think if I don't include them, that makes it incorrect. I thought for a moment that it was implicit from the presence of dk that the list is at least k. That would only be true if the k was on the right of the condition, not on the left. So this is why I think you have a point, and I should update that slide to include the length, just like I did here, actually. I should just make sure that the length also appears in the condition. Yeah, thank you for that. There is actually a deeper reason why mentally I forgot about the length that is justified, and that we'll come back to in the models. But nevertheless, it is a mistake and I will fix it. Okay, so let's go to unigrams, which is the case where n equals 0. Yes, unigrams. It's n plus 1 in front of grams. So unigrams, n equals 0. What does it mean? It means that I'm looking at 1 gram, and what my Markov rule tells me is that the probability that the kth term is dk, conditioned on the fact that the length is at least k and all the previous terms, actually is the same as the condition that it's dk based on the length, ignoring the previous terms. I dropped them, I forgot them, I don't even remember. This all goes away. So I'm basically just looking at the probability that the next term is dk, just knowing that it exists, right? The length being k means there exists a term at position k. All right, so the next thing to ask whenever I have a very ugly formula is, where are my parameters? Well, as you know by now, the uppercase things are not parameters. These are random variables. The real parameters are the lowercase ones. These are the real mathematical variables. The only thing I can see here is really k, that is one parameter, and dk, that is the other one. I'm going to assume it doesn't depend on k, right? This is also an assumption we make, is that whatever position in the document I'm at, the probabilities will just be the same. So I assume it doesn't depend on k itself, but it does depend on the term. It does depend on dk. So this is why I'm going to call this entire thing right there, p dk, like p computer, p information, and so on and so on. Right? I just have as a subscript the term that I'm looking at. All right, so far so good, right? And again, I made an assumption. This does not depend on k. Strictly speaking, it should have depended on k, right? But it doesn't, because we assume it doesn't. Okay, so what does it look like, a unigram model in practice? Well, I need these probabilities for every term. So you can look at that as a two-column table, where in the first column you have the term, and in the second column you have the probability of the term. That's called the unigram model. So basically you have the probabilities on the right that should sum to, yes, 1, exactly. So it sums to 1 if everything is okay, at least if I have all of my terms. So all I need to give you is the list of all terms. Maybe it's 500,000 of them, right? It can be huge, right? But this is a list of terms, and these are the probabilities that sum up to 1. Okay, so I could also represent that with this small automaton like I did before, where you have this note here and you just keep cycling on the next term, right? Every time it's the probability of the next term you pick. Of course, you have to multiply with 1 minus p stop every time, right? So implicitly, if you want the real weights in there, you must multiply all of them with 1 minus p stop, right? And the p stop is right there. So it's when you sum everything here, you get 1. So here, again, I repeat, there is an implicit renormalization on 1 minus p stop in that table so that it sums to 1. And we like to separate the stopping probability from the probabilities of the terms. So in other words, we decouple the probability of stopping from the probabilities of the term. So this is why by convention, we make it sum to 1 right here, and then implicitly multiply with minus p stop there. Is that clear? It's really just a convention, really. Okay, so basically what I mean is we have a machine right there. We can start right here, and we can just iterate, and then at some point stop, and then we have a document. Right? It's actually pretty cool when you start doing that, but this is how it works. All right, so what is the probability of the document being D1, D2, D3 then? Can you tell me? Somebody on Zoom, maybe, in the Zoom chat? We are under the unigram model. Ah, here, a raised hand. Go ahead. Yes. Would you also add other factors? What about the p-stops? So what would you add then for the p-stops? You're not wrong. I will come back on why you're not wrong. But so if there were the p-stops, what would you add? Yeah. Okay. So okay, I need to repeat for those on Zoom. So what you essentially said is that it's PD1 times PD2 times PD3. And you also need to multiply with the stopping probabilities. And as you said, it's going to be 3 times the 1 minus p stop and once the p stop. And this is what you get. Do you agree with that? Awesome. Do you agree too? Is it also what you have said? Okay. So yes, indeed, this is what we have. I'm just now weighing in my brain if I should already tell you now why it's not wrong to drop the p stops. Let me keep it for later. I will keep it for later. Let's keep it a mystery for now. Why did I also drop them on an earlier slide, and why did you also drop them? Because actually, you're absolutely not wrong. In the implementation of the unigram model, it's really PD1, PD2, PD3, and that's it. Right. But again, I come back on why that is. Okay, so now one more thing. We are in the list of words model. Right? There is an order. So normally, this is what we are looking at. We are looking at a random variable that is this T star that basically means a sequence of terms of arbitrary length. This is the list of word model. However, in the unigram model, what we like to do is to actually not look at the list of words model, but the bag of words, the third one. What does it mean to go from the list of words model to the bag of words model? What do we drop? Not the 1 minus p stop, not yet, something else. What do I drop, or what do I forget about when I go from the list of words to the bag of words model? Yes? The positions, yes, exactly. So you basically lose the order in which you find the words, absolutely. So you still know how many of each there are, right? This is the bag of words, but you don't know anymore the position they belong to. So what's important to understand is that the list of word model is more fine-grained. It has more information. The bag of word model is like zooming out a bit. You zoom out and forget a bit of information. So it's like a random variable that is a bit more coarse than the list of words model. You zoom out. So in a way, this random variable here is just a zoomed out version of that one, because you basically put together all of the documents that have the terms in the same occurrence, but maybe in different orders. They will all correspond to the same in the bag of words model. For example, if I give you a document with foo bar foo, and bar foo, these are 3 different documents in the list of words model, but they are the same in the bag of words model because this is twice foo and 1 bar. Right? You agree? So basically, what's happening there, a mathematician would call it, we quotients by an equivalence relation, and we obtain the quotient set and blah, 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 blah. So I'm not going to go that deep in here, but basically this is pretty much what it is, right? We group the documents that just differ in the order of the terms, but otherwise have the same occurrences, and then we get the bag of word model. When we do that, we can then very easily design the probability formula that belongs to it, meaning that the probability of having twice foo and once bar is the sum of the probability of the individual orders. Right? So the probability of foo2 bar 1 is probability of foo bar times probability of foo bar foo times probability of bar foo. This is exactly what this formula here is for. D prime here would be a bag, so it's a vector of numbers, the vector of the occurrences. Here, that would be the list of word semantics, and I sum over all the possible orders of my terms that match my bag. I sum over them. Okay, so far so good? Okay, so we are just going to lose the information on the order of the terms. And the cool thing in there is that it's not going to take a lot of effort to do that, because it turns out that this is just a multinomial distribution, and mathematicians in combinatorics know that extremely well. They even have a formula for it, and we are just going to trust them, right? This is not a combinatorics course. This is the formula that we're going to trust them on it. I'm not going to show it. This is called the multinomial distribution. You might know the binomial distribution, right? This is basically when you have Bernoulli trials, like you keep tossing a coin like head, tails, head, tails, head, tails, and then you count how many tails, how many heads, right? So if you do it with 1/2, what you basically obtain, one example of what you can obtain is the Pascal triangle, right? If you have multiple labels and how can I explain that? We take a coin and throw it 3 times. So what I can have is 8 possibilities: heads, 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 tails, heads, tails, heads, heads, tails, 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 head, heads, tails, heads, tails, 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 head, and tails, tails, tails. Right? These are the 8 ones. And then the binomial distribution means you zoom out from that, looking only at the number of heads. What can it be? It can be 0, it can be 1, it can be 2, or it can be 3. Right? And so then what you need is, if you have a uniform distribution over the original heads and tails list, right? It's uniform, so it's 1/8 for each. But now, if you consider that there are, let's say, 3 ways of obtaining 1 tails, it can be either first, second, or third. There are 3 ways of obtaining 2 heads, because that's 1 tail. But there is only 1 way of obtaining 0 tails, or everything tails. That gives us 1, 3, 3, 1. You know, it's x plus y to the power of 3. It's x to the power of 3 plus 3 times x squared y plus 3 times x y squared plus y cubed, right? It's all these binomials formula in the Pascal triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Who also already saw that triangle? Right? It's quite famous, right? And that triangle is just the binomial distribution if the probabilities are 1/2, 1/2 on heads and tails. This here is just a generalization of that in the case that it's not just heads and tails, but it's like instead of tossing a coin, you have a die with 6 faces or whatever number of terms we have. So this is pretty much what it is. And what's going on here is that now the probability that a document is specifically this document right here, which is a bag of words, is going to be, let's go to the part that is the easy one. This you recognize, right? So this is the probability of not stopping as many times as the length of the document, right? Here, this is the probability of stopping at the end, right? So this is what we've seen before. This we've also seen, right? In our example, that was PD1, PD2, PD3, right? So this is the product of the probabilities of the individual terms. What is that power right there? What does TF mean? Yeah, how is it called? term frequency, exactly. So this is the term frequency. So you have the probability that the next term is t as many times, so it's a product, so this is why it's a power, but as many times as the term frequency of t in document D. That makes sense, right? So for example, if you have the term information 3 times in the document, then you're going to have P information, P information, P information. If you have twice the word computer, you're going to have P computer, P computer. If you have 0 times the word cat, then you just don't have anything. Power is 0. For whom is that clear? All right, and on Zoom, are you following on Zoom? A few raised hands would be nice, just checking. All right, very nice, okay. Cool, so basically that means that this part right here, you get, well, of course, this is the list of words part, right? So this here is the probability that a specific order is obtained with exactly these occurrences, right? Why doesn't it depend on the order, the product? Because I said it's the probability of a specific order with these occurrences. Why don't I see any order in there? Yes?
I think we made an assumption that it doesn't depend on the order or on the position.
And what is this assumption called? It's the Markov rule, remember? From the moment we assume the Markov rule, plus we said the P dk does not depend on K, this is when we assume that. So it's just like when I tell you if I'm tossing my coin 3 times, then the probability is uniform, the distribution. So it's heads, tails, 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 heads, tails, or heads, heads, tails. It's always 1/8, 1/8, 1/8, 1/8, but for each one of the positions. So this is why this huge product on the right is the same no matter what the order is. So if I have the words like foo bar, then the product for foo bar, for foo bar foo, and for bar foo is just going to be the same. However, how many times did I say it? I said bar foo bar foo, and foo bar, 3. So I need somehow to multiply with 3 to take into account the number of combinations I have. This is what we have here. This correcting factor is exactly this multinomial distribution. This is the Pascal triangle. This is the Pascal triangle, but generalized to any number of labels beyond 2, right? So this here is just multiplying the probability of a very specific sequence of terms that have an occurrence, but I have to multiply it with all the possible realization of my order. This is my correcting factor. And then I get the probability that I get this bag of words document. For whom is that clear? All right. Okay. But anyway, it takes a bit of trust. So just trust me that this is the multinomial distribution. And that's pretty much it. Now, let me just make an observation on that slide right here. The observation is this. If you look at that part here, this is just, you know, you could put parentheses right here, right? It's just the product is for here. So this is a part, and then you multiply with this. This here only depends on the length of the document. So if you were to compute the same thing all over again and all over again and all over again for a specific document length, this would be a constant, right? So this is why actually in practice, and I'll show you why in the information system later, because what we are going to compute on is going to be the query, and the query is constant. And that's the reason why all of that is dropped when we compute the weights, because there's going to be weights and there's going to be scores in the same way. This here is just dropped because that's just a constant that only depends on the query. This is the reason why I made the mistake of dropping the 1 minus stops and stops on a previous slide. This is probably similar to how you spontaneously drop the 1 minus p stop in what you said. There is a reason. This is really that this is just a constant. And in practice, we just drop them for the purpose of information retrieval. But it will be even clearer when I tell you how this is used for information retrieval, of course. So we just observe this only depends on the length of the document. All right. Okay. So now, in the general case, how does it look like if now we don't assume n equals 0, but maybe higher values of n? What is the main difference? Well, the major difference is actually that in that case, we are literally stuck in the list of words model. We cannot go to the bag of words model. That's the main thing. In the unigram case, we could use this multinomial to go to the bag of words. If n is higher, you cannot. We are stuck at lists of words. So this is a Bigram model. It means that now I have an extra column. This is the previous term, the last one that I produced. This is the current one that I'm picking from. And every time I have my probabilities. Note that this sums up to 1 right here within the same previous term. This sums up to 1 right here. Actually, it doesn't, and I should fix that. We'll assume for the, just pretend that this sums up to 1. And this corresponds to B. Actually, I don't know if you ever saw Bayesian networks. If you haven't, you will see Bayesian networks, but this is pretty much the sort of data you find in a Bayesian network, where you have the priors, and then you have the updates to the current variable, right? So if you ever do causal models with data science and so on, and this is something you will see over and over again, sort of transition tables. Okay, but basically what it means in terms of formulas is that now with the bigram model, right, it's not the unigram anymore, the probability of having document 1, 2, 3 in this order, because as I said, we're stuck with the list of words, right? So it can only be a list. Is the probability of continuation times the probability the first term is D1, then 1 minus P stop again. The probability that given D1, the next one is D2. 1 minus P stop, we have a third one. The probability given D1, given D2, sorry, because I forgot about D1 by now. The next one is D3, and then I stop. For whom does that make sense? All right, and who understands that this is list of words and we cannot go to the bag of words in that case? All right. This is really because in the case of the unigram, we don't have any memory at all, right? No matter what step you are in, you don't see any path. This is where we can go to the bag of words. Okay, so now here's what's going to happen. Imagine, it's a thought experiment, right? Imagine that we take the documents in our collection. At the ETH library, we take all the books, the Sherlock Holmes, the information retrieval book, the algorithms and data structure textbook, like all of them. We use these books and we basically generate these tables out of the books. It's easy, right? For example, in the case of the unigram, all you need to do is count, do the statistics, count the term frequencies and divide by the number of terms. And then that's called maximum likelihood model, right? And then you get, based on the term frequencies, you deduce the probabilities, right? Is that clear? You just count the number of terms in the book and renormalize to 1, and that gives you the probabilities. Then you can do, so this is unigram. You can do the same thing with bigram, right? Then you just need to do the same thing, but with sliding windows of 2 terms. And every time you have a new pair of terms, you just upgrade, add 1 to here, and at the end you renormalize to 1, and you renormalize to, well, 1 in order to make it normalized, right? Who could do it programmatically? Okay, well, you will in the exercises. That's the good news, and you will see it's quite fun. So anyway, programmatically, you can generate for any book, for any document, a model. And then you can use that model to generate fake documents. And these are a few cool examples, and you will see why this is really, really fun to do. 1 gram, 2 grams, 3 grams, and 4 grams. You can see how it looks like. And it's quite amusing. So you see with 1 grams, this is really like the bag of words things, like it's just the dropping words without any consistency. There is no link between the words because we have no memory. To him, swallowed, confess here, both which of save on tray, I can try to do it like a theatrical accent, but I'm still not going to make any sense, right? Because this is unigram. Then 2 gram, you start seeing some connection. Why it does? So this is a bit of, like it's when English was closer to German than it is today, right? You actually had the ST as the second person back then. Why does stand for like canopy, blah, 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 blah. But what's extremely impressive is as soon, it's still a small number of 4, right? It means you remember the previous 3 words. King Henry, what? I will go seek the traitor cluster. Excellent, I don't know how to pronounce that thing. Some of the watch, a great banquet served in. It cannot be bad. So that sounds incredibly real, right? So you see that this value of the parameter n that you can actually set determines that sort of thing. And so then you can have a lot of fun and download corpuses or text from the internet and just generate texts like that. You can do it with music. Now it's even done with machine learning these days. So it's taken to the next level. But this existed already 20 years ago before machine learning was even as popular as it is today. Right? And it's the sort of thing that really just takes, let's say, 1 hour to do. And you can have things like this. Okay, so that's the fun part. But of course, this is an information retrieval lecture, and we have to use it to be a system. So how does it work? Well, now we have this query queue that the user has just entered on their computer. And we are thinking as follows. Imagine that we picked one of the books in the library, wrote a computer program, built these matrices and probability transition matrices. And then we built the model like that. And then we push the button in order to trigger the generation on a text based on the book. And surprise, surprise, what do we get? The query queue that the user has just given. That's an enormous coincidence, right? But it just happened. So imagine that this actually happened by an extraordinary chance. You happened to have generated exactly the query that the user has input. And now my question is, what document of the library was the most likely to have been selected in such a way that by chance it generated exactly query queue? Now you realize that this question right here is pretty much the umbrella and rain question, right? It happens that today I have my umbrella. Can you deduce the probability that it's actually raining outside? This is pretty much the same idea. So it means that we have this mental model of picking a document, generating at random, generating the model of that document, and we happen to generate the query. This is a query likelihood model. We go all the way back and ask, what is the document that was the most likely to have been taken? Now, to be clear, you could argue, yes, but the chance that you generate the query are extremely small, right? But here's the thing, maybe with this document, you had 1 chance in a trillion to generate the query. But with this other book, you had 1 chance in a quadrillion. And with another one, a chance in a billion. Which one wins? The one in a billion, right? So although these are very small numbers, you still get something to compute that allows you to compute scores and rank. And the way this is done is, and now we are back to what we were doing last week, right? Because now you know the base formula by heart. Again, I'm looking for the likelihood. So what is the document most likely to have generated query queue? Well, I use my magical Bayesian formula, swap them, the probability of Q given D, and then, of course, these correcting factors. Now comes the cool part. As always, we love when we just get rid of some of the factors. This is a constant, so this is what we need to sort by, right? But this is a constant, depends on Q, so we can drop it. This here, the probability of the document, if we assume this is a uniform distribution, like I went to the ETH library and picked a book at random. This is always 1 over the size of the collection. We get rid of it, so we just really need to sort by that. Right. Now, what is that? It's the probability that based on the model of document D, so a specific set of transition matrices, what are the odds that we generated specifically Q? Well, this is it. We already computed it. That was our binomial distribution. So in the case that this is a unigram, right? So this is it. And what's more, now you understand, I can just drop that because this is LQ here. It's the probability of generating the query Q. So this here does not depend on D, right? So I can just drop all of that, right? Okay. Oh, I think now I realize I should probably, oh no, here. So the D, because I was asking like, where is D then if D is not there? D is actually here. Because it's, if you look at how the PT was computed, then this is where the original book comes from, right? All the rest just depends on the query. But PT depends on the document D, because as we said, you can approximate the probability of the term being a specific term T with the term frequency in the book that you picked, right? So this is where D is. Okay, so this goes away and D is right there. Okay, did you follow, or was I too fast here? Right, so again, I repeat. We have a query. We picked a document at random in the collection, generate the model, push the buttons to generate the query, which is according to these probabilities right there that we generate a query. But now we know Q and we want to find D. So we swap the two with the Bayesian formula, right? So the probability that it was document D given Q. We saw that since these two things are constant, we can just swap for free. Basically, this is a free swap. Just swap them. And that means that these are our weights. This is our score for documents D. And we notice that a lot of parts depend only on Q and can go away. This is where the dependency on D is, right there, because PT comes from the model based on document D. It was approximated statistically by just counting the occurrences of term T in document D, renormalizing to 1. Okay, so this is what happens, and this is the computation, yes? That's a very good observation because yes, it drops as well. Yeah, I forgot to say it, but absolutely. You can get rid of this and you can get rid of that. Isn't that wonderful? So this is why you don't even need to care about the multinomial thing, right? Because this anyway is forgotten. Why? Because this factor here is specific to the query itself. So it doesn't affect the score of the document. What that means concretely is that to compute this absolutely ugly thingy here, all you need are the PTs that correspond to your document transition matrix. That's it. And this is why the intuition you had saying earlier, okay, this is PD1, PD2, PD3, is exactly the right intuition, because in the end, this is exactly what we compute in there. So again, if I say it again, this is the only thing that we really need to compute. All the rest goes away. This is just that. So in essence, it's just a product of probabilities. Period. That's simple. For the unigram model, of course, because if you go for the other ones, it's more complex. Yes? Exactly. It's not the same probability space as last week. Okay. So what I did this week was that actually remove the little wheels of the bicycle, basically. So I basically just reasoned in terms of random variables. And the omega space was more abstracted away this week, right? Last week I gave it because that was quite unintuitive, the idea of the relevance, even the document and a query. So I gave you an intuition of the omega space. Most of the time, when you do reasoning on probabilities, people tend to just not consider the omega space again. It's basically like some microscopic thing that is in the background that has the elementary events, and you just run your computations on the actual variables. Now, you could always build an omega space. You could also always build one. So if we go back, so it always, we need to pick a specific place, right? So let me take the document as a constant. So let me just fix the document. I have one specific model. So now the only thing that varies in there is basically the terms. So you could consider that your omega space, since you only have the random variable corresponding to query Q, you could take as omega the set of the values in Q, right? Trivially. If you only have one random variable, you can canonically identify the omega space with the target set of the variable, then you just have a bijection. So this is what you can do, right? So in theory, for one specific model, you could say the omega space is just the set of the documents I can generate. Now, where it gets complicated is when you stop fixing the value of the documents. So now when you go to these formulas right here, this is where it gets complicated. Because now this omega space that you consider when you say the probability of a document D based on a query Q is absolutely gigantic. Because now you have to consider every elementary event in that omega space corresponds to each way you can pick a book in the library and generate a query. You're looking like at it's massive. It might even be more than atoms in the universe, right? So it's an incredibly big omega space. And in Bayesian reasoning, what people do very often is that they have a random variable with an underlying omega space. Then you add more random variables, but actually it has an effect on the omega space when you do that, because implicitly you make the omega space even bigger retroactively. And this is a bit of mental gymnastic when you do that. And in fact, when you reason in terms of Bayesian statistics, it's something that can be controversial, in some aspects of the scientific community, precisely because you forget about the omega space. And in particular, this is why when you talk about the documents, the term used is not the probability that we took document D, but the likelihood that we put document D. So you see that reasoning is actually abstract and really almost puts the omega space out of the picture. And I would say that when you arrive at the point of asking for the omega space, and like I told you last week, like with a quintillion people asking tasks and so on, this is almost becoming a philosophical debate, I would say, on the validity of Bayesian reasoning. And that is way beyond the discourse right here. But it's a very, very interesting debate on the whole validity of Bayesian reasoning and Bayesian networks.
But so that we can say that, so here we said that this means the probability on the left means that document D generated Q.
It's the probability, more exactly the likelihood, that you picked document D, knowing that whatever document you took gave you Q.
But to interpret, we have to know the probability. So to be able to say that this formula says that,
Yeah, that's exactly, the trick about Bayesian reasoning is that in order for this formula right here on the screen to be valid, you need an omega space. It's just that when we do these reasonings, we tend to not really instantiate the omega space. It's there, it's out there, and we just go ahead and write the formula like this, hoping that it works. But the philosophical criticism is precisely on the relevance of such an omega space that is kind of made up and in our minds, right? I'm not sure if that makes any sense, or this is the answer you expect. It helps a bit? All right. For the purpose of the lecture, don't go into the philosophical debate of Bayesian reasoning. Just assume that there is an omega space behind that. It's an omega space that might have octillions of elementary events. It's absolutely enormous. And every elementary event in that omega space corresponds to you going to the ETH library, asking the librarian to give you whatever book they want at random, sitting in front of your computer, generating a model, and generating a query that comes out of it. This is an elementary event. And you will agree that what I've just described gives you D and Q unambiguously. D is whatever you got from the library, and Q is whatever your computer outputted. Do it an octillion times. This is your omega space. And then you can do this reasoning saying, okay, now the user gives query Q. So you take the subset of this octillion elementary event where the query is Q, and you look at the relative size of the D compartments, and you pick whatever document has the biggest. Now, this is something visual, because of course you're not going to do that. There's no way you will build this octillion size omega space and directly look at the relative weights of the sets, right? Which is why, instead of building the omega space, we write down these Bayesian formulas and do all of this mathematical gymnastics. Does it make sense? Really? Okay, awesome. But this is, this is a very interesting question, and you do have in the scientific community the debates on Bayesianism and the relevance of Bayesian reasoning, because there are assumptions like that. All right. Any other questions? All right. So we have this, all right? So this is the model we want to sort on. We realize we can drop this and this. So it comes down to this formula. We drop this, we drop that. We just multiply the few numbers. That gives us the scores, and we just sort them or pick whatever the scores are the highest. Now, what I wanted to show you, and this is again the same wow moment that we had with the probabilistic. What's going on with the screen here? Is it completely bugged? Well, as long as this screen still works, that's fine, but this console just stopped responding. Anyway, just wanted to check the time to make sure that, oh, we're almost done. So the one thing I want to point here on that slide is that in the same way as last week, we found the IDF in the slide. The one thing we find here is the TF. We are basically ranking our documents based on weights that involve the term frequency. This here gives a formal justification to having the term frequencies in the vector space model, right? So the IDFs last week, the TFs this week, and then you can do your cooking using both of them, right? Okay, so the way we compute them in practice is that we don't just divide the term frequency, renormalize, we smooth, as you know, because in practice, this would be maybe the distribution. But when you actually do measure, you might miss a few terms. So you smooth a bit by adding a bit of noise all over the place in order to get something that is more spread all over the set of terms. Which is why instead of just taking the term frequencies and renormalizing, typically we like to do some cooking with a bit of term frequency and a little bit of collection frequency. Some people argue that this kind of simulates the IDF for some reason. So this is why this can also be used as a proxy for the inverted document frequency. Okay, but I'm not going in depth regarding this. So this is the query likelihood model. There is also a document likelihood model that is the same thing the other way around. Needs a bit more work because then you need to have some relevance feedback, but I'm not expanding on that. And finally, there is a third category of research where you generate models from both sides, and then you compare the query model and the document model with some metrics. But this is way more advanced than what we've done today, right? So this is where it stops. Again, that's all on the master's level, so more complex than in previous weeks. Have you been following today? Okay, who is going to do the exercise and actually try to generate fun text? The TAs will do it with you too. You will see it's actually fun. I think they want to do it with coffee, right? I think it's Andrea who told me that. I think that Andrea wanted to generate documents involving coffee, and apparently they have a lot of fun preparing this. So you will see. Anyway, this is where it stops for me. There is no more material. Please read the chapter in the book. There is a chapter in the book. If you didn't understand what I've been telling you, then read the book. Maybe they do a better job. I'll see you next week for the wrap-up and with a quiz. Right, so thank you very much. Enjoy your exercise session.